Welcome to today's session, where we will explore the Poisson distribution, a fundamental discrete probability distribution. Over the past few sessions, we have examined various types of probability distributions, both continuous and discrete. We looked at the normal distribution in detail, which is a key example of a continuous distribution. We also studied the binomial distribution, a classic discrete distribution. Building on that foundation, today we turn our attention to the Poisson distribution, which is especially useful for modeling the number of events occurring within a fixed interval of time or space. The Poisson distribution. It is a discrete distribution related to probabilities of events which are extremely rare, but we have a large number of independent opportunities for their occurrence. For example, the number of accidents occurring at a particular place in a city. This distribution can be derived as a limiting case of the binomial distribution by making n very large and p very small, and np as fixed, say, lambda. The probability of success in a binomial distribution is given as n choose xp raised to xq raised to n minus x. The equation for Poisson distribution is lambda raised to x times e raised to minus lambda divided by x factorial. The Poisson distribution is particularly useful for modeling rare events that occur independently over a fixed period or space. This distribution emerges from the binomial distribution when the number of trials is large and the probability of success is small, while keeping the product of these two parameters constant. The formula presented here illustrates how we can calculate the probability of observing a certain number of events, which is crucial for understanding risk in various fields such as insurance and quality control. In this slide, we will see the derivation of the Poisson distribution as a limiting case of the binomial distribution. The equation for binomial probability distribution is shown here. The probability of success in a binomial distribution is given as n choose xp raised to xq raised to n minus x. Expanding the expression n choose x, we get n times n minus 1 times n minus 2 times up to n minus x minus 1 divided by x factorial as shown here. On examining the expression, we can see that there are x times np s. We can take out the np raised to x as shown here. As n tends to infinity and p tends to 0, np tends to lambda. Substituting for np equal to lambda and applying the limit, we get the expression as lambda raised to x times 1 divided by x factorial times limit n tends to infinity p tends to 0 q raised to n minus x. We can see that q raised to n minus x is q raised to n divided by q raised to x. We have seen that q raised to n minus x is q raised to n divided by q raised to x. Substitute 1 minus p for q using the relation q plus p equals 1. As n tends to infinity and p tends to 0 in the limiting case, we can write p as lambda by n and q as 1 minus lambda by n. Substituting these, we get the expression here. When the limit is applied to the numerator of the expression, 1 minus lambda divided by n raised to n divided by 1 minus lambda divided by n raised to x, we get e raised to minus lambda. The denominator reduces to 1. We will show the derivation of these results in the next slide. This slide continues the exploration of the Poisson distribution by examining the limit of the expression as n approaches infinity. The expression 1 minus lambda divided by n raised to n is expanded as a series shown here. Cancelling out the n's in the nominator of each term, we get the expression shown here. Applying the limits n tending to infinity, the expression limit n tends to 0, 1 minus lambda divided by n raised to n reduces to the series shown here. On examination of the series, we can see it is the expansion of e raised to minus lambda. Similarly, the expression limit n tends to 0, 1 minus lambda divided by n raised to x is expanded, and the limit n tends to infinity is applied to the series. Since the n's do not get cancelled as in the previous case, all the terms containing lambda by n reduce to 0. In the limiting case, the expression reduces to 1. The mean of the Poisson distribution is a critical concept, represented by lambda. This slide outlines how to derive the mean using the probability mass function. Mu is equal to the summation of f subscript I times x subscript I from 0 to n. Substituting for f subscript I, we get the expression shown here. Substituting the values of x subscript I equal to 0, 1, 2, 3, etc., up to n, we get the expression here. Simplifying and taking lambda times e raised to minus lambda out, we get the series as shown here. On examining the series, it is evident that the series is the expansion of e raised to lambda. Cancelling out e raised to minus lambda and e raised to lambda, we get the mean as lambda. Variance is another important aspect of the Poisson distribution, and it is also equal to lambda. This slide presents the derivation of the variance, illustrating how it reflects the spread of the distribution around the mean. The expression for the variance is given here as sigma squared equals the summation from I equals 0 to n of f sub I times x sub I squared minus x bar squared, which equals the summation of f sub I times x sub I squared minus lambda squared. Substituting the values of x subscript I equal to 0, 1, 2, 3, etc., up to n, we get the expression here. On applying the simplification as shown, we get the expression here. On rearranging the terms with one of each term together and the remaining separately, we get the expression here. Taking out lambda times e raised to minus lambda from the first group and lambda squared times e raised to minus lambda from the second group, we get the expression here. On simplifying, we get the summation of f sub I times x sub I squared as lambda plus lambda squared. This result, when substituted into the expression for variance, gives lambda. Hence, the variance is derived as lambda. This slide introduces practical applications of the Poisson distribution, particularly in scenarios involving counts of events over time or space. Examples such as machine breakdowns or product defects illustrate how the distribution can be utilized in quality control and operational efficiency. Understanding lambda as the average count allows businesses to predict and manage risks effectively, making the Poisson distribution a valuable tool in various industries. Cumulative Poisson probabilities are given in Poisson tables. An extract of a Poisson table is given here. Probability values corresponding to particular values of lambda and x can be read off from the table. Problem 1. If the probability that a heat-treating batch will be defective is 0.01, what is the probability of 2 bad batches out of 250? What is the probability of 2 or fewer? Lambda equals n times p equals 250 times 0.01 equals 2.5. Since the probability table gives cumulative probability, the probability of exactly 2 bad batches equals the probability of 2 or fewer batches minus the probability of 1 or fewer batches. The probability values are read from the table corresponding to lambda equal to 2.5 and the values of x equal to 2 and 1. The probability of exactly 2 bad batches can be directly calculated using the equation for the Poisson probability density function shown here. Problem 2. The average count of billing errors at a local bank per 8-hour shift is 1.0. What is the probability of 2 billing errors? Probability of 1 or fewer? The probability of 2 or more? Solution. Lambda equals 1.0. From the table for the Poisson distribution, p of 2 equals p of 2 or less minus p of 1 or less, which is 0.9197 minus 0.7358, equals 0.1839. P of 1 or less equals 0.7358. P of 2 or more equals 1 minus p of 1 or less, which is 1.0 minus 0.7358, equals 0.2642. Problem 3. The probability of a bad reaction from a certain injection is 0.001. Determine the chance that out of 2,000 individuals, more than 2 will get a bad reaction. Lambda equals NP, which is 2,000 times 0.001, equals 2. P of more than 2 equals 1 minus P of 2 or less, which is 1 minus 0.6767, equals 0.3233. Problem 4. The following table shows the number of days, F, in a 50-day period during which X automobile accidents occurred in a city. Fit a Poisson distribution to the data. From the tabulated data, lambda is calculated as shown in the box. The equation for the probability can be fitted by substituting the value of lambda equal to 0.9 in the equation for Poisson PDF. The expected value of the failure for x equal to 0, 1, 2, 3 and 4 can be calculated using the fitted equation. A comparison of the expected values and the provided values is shown in the bottom table.